Section 16.3, the autoionization of water. One of the most important chemical properties of water is its ability to act as either a Bronsted acid or a Bronsted base, depending on the circumstances. In the presence of an acid, water acts as the proton acceptor. In the presence of a base, water acts as a proton donor. In fact, one water molecule can donate a proton to another water molecule. We call this process the autoionization of water. No individual molecule remains ionized for long. The reactions are extremely rapid in both directions. At room temperature, only about 1 out of every billion molecules are ionized at any given instant. Thus, pure water consists almost entirely of water molecules and is an extremely poor conductor of electricity. Nevertheless, the autoionization of water is very important, as we will soon see. The ion product of water. Because the ionization of water, equation 1612, is an equilibrium process, we can write the following equilibrium expression for it. The equilibrium constant is equal to the concentration of hydronium times the concentration of hydroxide. The term, the concentration of water, is excluded from the equilibrium constant expression because we exclude concentrations of pure solids and liquids. Because this equilibrium constant expression refers specifically to the autoionization of water, we use K sub W to denote the equilibrium constant, which we call the ion product constant of water. At 25 Celsius, K sub W equals 1 times 10 to the negative 14. Thus we have K sub W equals the concentration of hydronium times the concentration of hydroxide yields 1.0 times 10 to the negative 14 at 25 Celsius. Because we use proton and hydronium interchangeably to represent the hydrated proton, the autoionization of water can also be written as water breaks apart into proton plus hydroxide. Likewise, the expression for K sub W can be written in terms of either hydronium or proton, and K sub W has the same value in either case. Likewise, the expression for K sub W can be written in terms of either hydronium or proton and has the same value in either case. K sub W equals the concentration of hydronium times the concentration of hydroxide, or the concentration of proton times the concentration of hydroxide equals 1 times 10 to the negative 14 at 25 Celsius. This equilibrium constant expression and the value of K sub W at 25 Celsius are extremely important, and you should commit them to memory. What makes equation 1616 particularly useful is that it is applicable to pure water and to any aqueous solution. Although the equilibrium between protons and hydroxides, as well as other ionic equilibria, are affected somewhat by the presence of additional ions in solution, it's customary to ignore these ionic effects except for work requiring exceptional accuracy. Thus, equation 1616 is taken to be valid for any dilute aqueous solution, and it can be used to calculate either the concentration of proton, or if hydroxide is known, or the concentration of hydroxide if the concentration of proton is known. A solution in which the concentration of proton equals the concentration of hydroxide is said to be neutral. In most solutions, protons and hydroxide ion concentrations are not equal. As the concentration of one of these ions increases, the concentration of the other must decrease, so the product of their concentration equals 1 times 10 to the negative 14. In acidic solutions, the concentration of proton exceeds hydroxide. In basic solution, the concentration of hydroxide exceeds protons.